No, Toni, poseu-vos aquí. Aquí us he posat els meus pares i vosaltres dos i aneu aquí, que ja sabia que veníeu en parella. Oh. Okay, testing. Hi, do you hear me?
Yeah. Okay. Yep.
Can maybe show the room.
Very packed.
Small one.
Should we wait a couple more minutes, or?
As soon, I think the streaming is already starting, no?
No, let me check.
And
I can check.
after that.
Did you get my email, Andy? Yep. I'm checking the stream right now. Yeah, it's going. No, I don't see you, Marc. I guess that's.
Is it working now that you can see the slides?
No. Yes. It's starting up right now. Yeah, I guess there's some. Yeah, there's quite some lag, but.
Oh, great.
No, I'm looking at how distilling structure from imagery. I don't know what's going on here. It's streaming somebody else's PhD.
I have outsourced my thesis, you know.
This looks interesting too. It's on yeah.
Yeah. But you should be, so I think the streaming is not necessary for the committee members, because I think you are capable of seeing my slides, no?
Yeah.
Okay, so then as soon as Josh confirms that the system is working, then let's start. Oh. Thanks, Herman, also to attending such an early hour of the of the morning for you.
No, thank you guys for inviting me. Mucha suerte para la presentación.
Thank you. Yeah, shall we start? Okay. So, yeah, maybe.
Make the introduction, yeah.
Yeah, exactly. Yeah, give me the heads up.
So welcome everyone to the PhD defense of Marc Masana. I think that we shall start with the exposition. I've been told that it has around 40-45 minutes to present his work. And then afterwards there's going to be some questions by Terary and Yeah, please, let's
Hi, I'm Marc Masana, and welcome everyone to my thesis dissertation. In these first slides, I will explain the terms that I used in this. So to start with, inside the world of artificial intelligence, machine learning is a discipline that allows computer systems to learn in an automatic way. So in the last decade, deep learning and neural networks have achieved great breakthroughs in many computer vision tasks and are used generously across these theses. Basically, neural networks learn to perform tasks that by analyzing training samples to learn groups of filters at different levels and in order to solve the task at hand. So the task can be trained from scratch like a tabula rasa, but you can also exploit previously learned knowledge using fine-tuning. And with that in mind, like large pre-trained models have been used in the last years to obtain these huge models that are capable of doing large multi-purpose data set. And the idea behind it is that you can use, with fine-tuning, you can use that as your starting point instead of a tabula rasa or from scratch to learn a new domain or a new task that you want to solve and that can benefit from the rich features that the large model has. And when doing that, you end up learning a new task on the new domain, but you also end up with a big model. So being able to trade off these extra unrelated knowledge that the initialization model provides can be exchanged for computational efficiency. Also, we will be talking about lifelong learning. In this example, for example, we would like to train a network to learn to differentiate a type of dog. And maybe later down the road, we want that same system to be able to identify another type of dog, so we will train it on that. However, if we train the new task without revisiting the previous one, the first dog breed would be forgotten in what is known in the field as catastrophic forgetting. And if it's done repeatedly over a sequence of tasks, then the oldest knowledge usually can be lost if we are just doing fine-tuning from one to another. So in order to avoid this catastrophic forgetting, we can have systems that avoid it. Yeah. Finally, if we will have a system that has learned, for example, all of these breeds of dogs, it's a model that will be very good at identifying which dog you are showing. However, it only knows that. So when conflicted with, for example, let's say a chicken, it will very confidently say, hey, it's this kind of dog, because the system is not aware of the extent of the knowledge. So knowing the boundaries and being able to say, I don't know what this is something that is also desirable. And this is the part that detecting novelty is based on. So putting it together, we have lifelong learning of neural networks, detecting novelty and adapting to new domains without forgetting, which is the title of this thesis, and it's divided in 4 parts, which I will proceed to explain. So the first one is domain adaptive deep network compression. And as we were saying before, if we see here at the left, we see that we can train a large network with a large data set such as ImageNet, which 1 million images. And then we can use that learn task on ImageNet to initialize the network with those weights to learn a smaller target domain on the right and be able to reuse these rich representations instead of starting from scratch and the model being so big, maybe falling into overfitting due to the limited data. However, once we do that, we are stuck with this huge network that is capable to do the task that we want, but maybe it's very large, so maybe we don't need to have such a large network. So the idea will be that we will be able to compress the network, but we don't have to lose any accuracy in exchange for it. So mainly in domain transfer or domain adaptation, the three main benefits of it is that it's easy to transfer using fine-tuning. This benefit makes the training much easier. You can exploit the strong representations, and it solves this problem of having less data to solve a task. However, as we were saying, the network is large, the information can be redundant, or it could still be overfitting in some cases, and having a large network is not desirable if your application has to be applied into small devices or needs a limitation on memory or energy consumption. And this leads what the first part of the topic is. It's about pruning and compression, specifically low-rank compression. There already exists 4 main themes of work: the network pruning, efficient layer representation, node isolation, and parameter quantization, that all tackle the problem in different ways. However, what we are proposing is that we apply compression specifically for the case of domain transfer, since it's become very common to train your network from a pre-trained model on a large data set, and also the use of activation statistics in order to adapt to the new task that we are trying to solve. In general, the low-rank compression, the existing method that was already used, or it's our baseline, is the SVD decomposition. The idea behind it is that if we, for example, will talk about a fully connected layer with this common equation, we can take the weights of it, we can apply the SVD decomposition, and then when we have the decomposition, we can remove the dimensions that are less important in order to compare to the original matrix and obtain an approximation that it's close enough and that can be represented putting together the U and the sigma as an A matrix and the V as the B matrix, and they can be used in the following way, so that you replace the weight matrix by those two without any ReLU in between. And in total, the amount of parameters that are needed to do that decreases significantly. The more compression, the more benefit that you get from this. So if we will take, for example, BGC16, we will be replacing the 2 fully connected layers before the final one, and we would replace it by 2 pairs of 2 weight matrices that all in all have much smaller memory footprint, as we will show later. So knowing that that was the situation so far, our motivation was that if we take the original pre-trained model here represented in red, which was pre-trained on ImageNet, and we analyze the activation rate of the neurons, in this case in fully connected 7 in one of the layers, and we order the activation rate so that it's easy to see the curve. We see that in the case of when we train on ImageNet and then we test that on the same data set, then very flat. And that usually represents that all of the activations that have been learned have quite some use, or at least are used mostly 20% of the time, which is quite important, we assume. However, when we move into evaluating the same on the birds, flowers, or actions data set, we realize that they're very skewed, which is indicating that there's a group of activations that are rarely firing and therefore are not contributing to the prediction on the prediction. So this is important because it's telling us that these activation statistics have to be taken into account, because if some of them are not useful, then that means they can be removed. So here is when our proposed method comes, where we propose to do an approximation like we were doing before with SVD of the weight matrix of the layer, or each of the layers. And then instead of doing like in SVD, we're trying to do an approximation directly on the weight matrix, we do an approximation by doing the weight matrix with the activations so that we know which ones are more used. And this means that when we do that, we can reformulate the previous equation as a low-rank regression problem by taking C as AB transpose and Z as weights and activations. And the good thing about formalizing it in this way is that it has a closed form solution that we can calculate is given below. If we do that, then we can apply exactly the same that we were showing before for SVD, where we can substitute the weight matrix by two weight matrices that together have a much lower memory footprint. And the difference is that this approximation has been taking into account the activation statistics. We did some experiments, and here I show the ones where we did when we do the birds data set as the target domain. And as we can see in here, our method here in maroon performs better than the other methods, and it can be compressed up to 4% of the original weight matrix size without a significant drop in performance. If we will apply this compression in both FC6 and FC7 from BGC16, and we would do it not at once, but slowly each of them so that they can compensate a bit each other, then we can reach these results that we see in here, where we can see that in this part in here, we have that the accuracy stays the same for the task of birds and flowers, and even we improve a little bit the performance by compressing on the actions data set, which we assume is due to removal of some kind of noise of some type. And the compression, as you can see, is significant on the amount of parameters that the network needs. The scale on the y-axis is in millions of parameters. We also did some experiments, and we showed that we were doing also improving over SVD on object detection with the faster CNN framework, which was very popular at the time of publication of this part. And we also noticed that, as we said before, some compression can even improve some of the classes, allowing that both SVD and our method will actually improve performance on those classes by just applying the compression to it, which I think is interesting. All in all, the important takeaways are that when moving from a source domain to a target domain, if we can observe that the curves of the activation rates go from flat to skewed, that means that there's parts of the network that are not being used effectively and therefore can be pruned, and we propose a rank constraint regression problem in order to do that. We achieve higher accuracy, and we beat the state of the art at the moment, and actually we further used it later on a real world application for detecting polyps in medical imaging, and we were capable to modify a system so that it will be able to run in real time thanks to the compression gain that it was achieved. We will move a second. Sorry. So then we move on to the continual learning without any forgetting part. So it is important to know that now we were talking about standard supervised learning, or we were talking about domain transfer or domain adaptation transfer learning. So in these cases, we are either training from scratch or we are moving from a source domain to a target domain, but we ignored the source domain. We don't want to keep the performance in there. However, if we will want to be able to learn the new task and still be able to perform properly on the previous ones, then we either have to move into multitask learning, where we will learn all of the tasks at the same time, or we will move into continual learning if for some reason we have no access to previous data because we are learning it in a continual lifelong learning way, or because there's some other kind of limitation. And this is where we are moving now in the continual learning setting, where we assume that the scenario that we will be working on is the one where we have a sequence of tasks that we want to learn one at a time. But at the end of each of them, we should be able to perform well in all of the ones that have been learned so far. In that case, some of you might be familiar with some of the related work. Hard attention to the task, HAT, is one of the methods that was already tackling task incremental learning for continual learning, and it used the inhibitory synapses. So it's basically learns an embedding that is on the activations of each layer, and this embedding is gated by a sigmoid function so that tension can be learned, and each task can learn which activations are more useful or more important to be kept when you want to train. Therefore, every time that you're learning a new task, you have to keep an accumulative attention over the activations for all of the tasks that you've learned so far. And since you're using this sigmoid, which is trying to get as close as possible to a gate a step function, because that will be the perfect no forgetting, let's say, then you have to apply a modification on the gradient when you want to do the backward propagation to be able to train properly. On the other side, there's also another method, it's PACnet, and this method is basically masking the weights. It's not based on the activations. And the idea, as you see in here, is that you will learn your first task on all of the network. Then you will compress it so you are capable of pruning away all of the weights that are not necessary in order to guarantee that you have a similar performance as you would have without compressing. And then you would move on to the next task by learning it in the remaining non-pruned weights that are available, compressing again, and repeating the cycle over and over again until you've learned all of the tasks, or you run out of space and then you have to tackle it in another way. By reading this related work, we were inspired because both of them are good, but they were having complementary benefits that each other didn't have, which in the case of HAT, the problem is if you try to make the sigmoid function closer to the step, it was very hard to train, and therefore it was not desirable, so forgetting should be allowed, although it was very little. When we moved to larger scenarios, it became a bit more of an issue. But HAT was extremely effective in not applying any kind of, or a negligible amount of overhead on the network that you were applying to, so then therefore making it computationally effective. However, in the other direction, PACnet was not as computationally effective because the overhead was really large. Every time that you would add a task, you would have to get a bit for every weight in the network. But on the other hand, you will guarantee the no forgetting for sure. So in order to try to compromise, we tried to, we designed a method that was able to do these both things. So if we would imagine that we have a network where we are only allowed to use a binary mask on the features, then we end up with this situation where the first task represented in gray and the second task represented in green would not be able to share connections, because when you try to learn the second one, if you have connections to the first one, you will not be able to both see it on the forward pass and not modify it on the backward, because you only have a binary mask, so you have to choose either. The way that we propose that is that we will get a ternary mask, which is the base of our proposed method, where the idea is that you have three states where you can either mask completely an activation so that the filters affected by it directly are not modified but are also not used during inference. We will also have a second state that will be that it allows the network to neurons to be used on the forward pass, but not on the backward, so they could be, the information could be used to predict, but would not be used to update the weights. And finally, the third state is the normal one, where you can do forward and backward usually. And the way we did that is that we applied two masks, one to the forward pass and one to the backward pass. And I think that I could explain the equations, or we can go in depth later, but I think an example is a much easier way to understand what we are proposing. So imagine that we are having a network that we are training on the first task that we are seeing on the sequence. In this case, we will be able to both apply forward and backward pass normally, like the weights will not mask anything, because we are just learning the first task. There's nothing, like we're starting from a tabula rasa. So, however, when the second one arrives, by using the two masks, we are allowing that the connections in black, which were the ones that were needed for the first task, will never be modified by the backward pass, because they are masked on the backward pass, but they are allowed in the forward, so the knowledge that is represented in those embeddings is usable for the new neurons that have been added to the model. If we do that like recurrently on the sequence, the benefit is that we need to include less and less neurons over time if the tasks are relatively related to each other, because then you can reuse all of these embedding representations without modifying what you had. And then you can guarantee that you have no forgetting, which is a characteristic that could be desirable for a lot of problems. On top of that, since sometimes it was not so easy to learn with a binary mass, or the embeddings could sometimes be a bit strict, we added this task-specific feature normalization, where we basically learn a task-specific bias and a normalization factor that allows to adapt the previous neurons, like the previous activations, to the current ones that we've added for the new task. And this allows a bit of wiggle room for the embeddings that we are having specific to the task at hand, to be able to have a better inference and also speed up the training. In our experiments, we first show the overhead axis that we were talking before. If we see here, hat, which was already had very little overhead already, is comparable, it's in blue, it's comparable to our proposed method in yellow. If our method will not be using this last part of the feature normalization, then it will be the pink line, which it will be much smaller overhead. The y-axis in this graph is logarithmic, so there's quite a huge gap when there's each of the darker lines. And then PACnet, which has to have a bit for each weight per task, is at the top. So we can show that we are comparatively achieving a good overhead ratio, let's say. And most of the other methods that are also used in continual learning for task incremental learning are actually also in the same line as PACnet. So they're high there. They need at least to duplicate the network once, most of them, in terms of overhead. We also did a few experiments. I summarized them here on tiny ImageNet splits. So we used the typical random split. In that case, PACnet achieved a slightly better performance, but we considered that we were competitive enough compared to PACnet and HAT, which were the state of the art. And then we also proposed, because we realized that sometimes it's important that the tasks have a bit more meaning between them, and it will be more challenging when you receive a new task that it's slightly more different than the previous one, to do a split that will be semantically split, so that each of the tasks have a semantic topic in them. And we see in the results that we are also competitive. We get the best results in here by a little bit on PACnet and HAT. And we also show that indeed this scenario is a bit more challenging. And on the other hand, the scenario that will be a bit less challenging for all of the methods will be that if we have a good first task, that it's large enough so that we can get some strong representations, then it's easier to learn the rest of them in all cases. But in this case, we also show that our method beat the state of the art. In order to move from the scenarios that were with a bit smaller input size images, we also did an experiment on ImageNet where we also show that we got a better result on the state of the art, and therefore it was applied to a more realistic large input data set. So in conclusion, we propose a zero forgetting approach that it's basically based on masking the activations so that we can reduce the overhead instead of masking the weights. We also propose to use task-specific feature normalization, which we consider that it's something that could also be used in other methods when you have to do task incremental learning, and helps when you have to adjust to new tasks. And then we also propose a semantic task split for tiny ImageNet and starting from a larger task scenarios, showing that the first one is a bit more challenging, while the second one allows for robust representations and therefore has some other properties. Okay. And now moving on from this part. Until now, we were using the task ID on all of these continual learning methods. So for this new part, we are moving into knowing the task when you're training because you have the label and therefore you know which task it belongs to. But during inference time, you don't know which task you are validating, so therefore you should be able to perform well and predict from all the classes that have been so far. So we are moving from a task-aware or task incremental learning to a task-agnostic or class incremental learning. And at the moment, there were no systematic analysis of the existing methods. So what we did is a survey on the current state where we check the challenges and the methods available, and we do quite a long experimentation. So we evaluate on 12 methods and several baselines. But here I will talk a little bit about some of the most relevant experiments because in the thesis you will see that there's a lot more and the time is limited. So the basic first point that has to be noted is that there's a couple of challenges when moving to class incremental learning because you don't have the task now. So the typical game of being able to retain the knowledge and learn the new task, which is known as the stability plasticity dilemma in the field, generates what we consider were 4 main challenges for the class incremental learning, and that are packed into 2 groups of, or 2 pairs of 2. So weight drift and activation drift are the 2 sides of the coin, where whenever you're trying to learn the new tasks, you will be modifying the weights. When modifying those weights and not having access to the previous tasks, then the weights will be updated, and therefore the weights can drift, and that's when forgetting can happen. On the other side, if you try to put some restriction on the activations, as we were doing or explaining before with our proposed method in the previous section, and try to avoid the drift there, then the problem is you become too intransigent and you don't allow the weight change, which makes that the forgetting is not happening, but then you are not capable of learning a new task. And both are highly connected. On the other pair, inter-task confusion is that whenever you're trying to learn new tasks and you don't have access to the previous tasks, what happens is that when tasks are not being trained jointly, they don't know about each other, or they cannot learn the differences between both of them, so that when later you evaluate on both of them at the time, there's a lot of inter-task confusion because the tasks are not aware of each other at the same time of training. If you try to solve that with something like, let's say, exemplars, where you can do rehearsal, then the problem becomes the other side of the coin, which is the task recency bias. By applying exemplars, we will see also that it's a common problem. The latest task that you've learned usually ends up being the more dominant one. And therefore, you have a bias towards the last task, meaning that your performance go down on the rest of them. So in general, we have evaluated on these 12 methods. There's 3 families that we describe in length in the thesis. And basically, it's regularization-based methods, which are the methods that either put a regularization on the weights or use data in order to regularize the embeddings to be able to avoid forgetting. And it's basically the ones that are in the green zone, and that later, in some cases, are either extended from the distillation loss of learning without forgetting or EWC and pathing into remaining walk by adding exemplars. The blue group is the one that uses rehearsal, and basically it means that we will keep a small memory of samples from previous tasks that can be rehearsed during the training of the next ones, and therefore updated in a way so that there's a bit of balance and in trying to avoid the inter-task confusion. And usually those same methods that use exemplars, and also most of them have been using the distillation loss, which is a regularization loss, have some kind of method here represented in orange that does the bias correction group. And the bias correction tries to tackle the problem of task recency bias that we just described, trying to, in some way, be able to not put this strong point towards the latest task and be able to distribute it across the previous ones. So, since this is discussed in length in the thesis, I prefer to highlight some of the results that we got. One of the first things that we noticed is we did we check the regularization approaches first, and then when moving from task incremental learning, so when we have the task ID, to class incremental learning, when we don't have, and we are not using exemplars in this case, where most of these methods we see here were presented in this scenario where there's no exemplars, we see that the methods that are based on distillation are basically doing better performance than the ones that are doing, data focused are better than the weight regularizations. However, as soon as we put the exemplars into the game, then something happens, which is like a lot of these methods are basically overcome by fine-tuning, but the fine-tuning with exemplars that it's strong enough. This was already noticed by one of the methods that we will be comparing, which is IL2M, but we also confirmed it during all of our experiments. So in the scenario where we have exemplars, a lot of the methods like EWC or path integral don't benefit as much of having exemplars as if you will just use the exemplars and drop the EWC loss for it. Regarding bias correction methods that try to tackle task recency bias, we also showed here that on the top there's the confusion matrices for the tasks, and on the bottom there's the confusion matrices for the classes. All of these is on a CIFAR 100 for 5 tasks on ResNet 32. And we can see that each of these methods tackles in a different way the task recency bias, or for example, in the case of EIL or Lucid, we can see that even if they tackle the task recency bias, making it lower than iCal, which is the method that it's not that directly tackling the problem, we reduce the inter-task confusion in previous tasks, but the last one that we have at hand, it's still highly biased in both cases. And it happens the same as you learn a new task, the latest one will be slightly biased while the previous one not. And BIC ends up having a bit like overcompensating, because a lot of the experiments we were seeing that in order to avoid inter-task confusion on the last task, it was achieving no confusion in the last task, but it still was not compensated correctly all of the previous ones that have been there. So this is an interesting point. And then we, of course, also analyzed all of these 12 methods on the common scenarios of Sci400 with 10 tasks on the left. And with 11 tasks on the right, where we will have an initial first task of 50. So we have a larger first task, similar to what we did in the previous chapter. And we realized that all of the bias correction methods clearly outperform the others. But also we noticed that some of those methods benefit a lot from having a first initial task, such as Lucir. Lucir and iCarl, if they have a very good first task that has a rich representation, perform much better than if they have a worse first task or a bit more overfitted one. Also, since we had not seen that there was much comparison on this, we decided to make a comparison with different networks that have been famous, like very classic from 2012 on. And we realized that the networks that we're not using skip connections, iCarl was the method that was having better performance, while when we were moving to networks that have skip connections, PIC was the best method. I mean, most of them can be close, but it's interesting to observe that for different architectures, the performance rankings of the methods change completely, so the order of the ranking is different. We also did an experiment on a large data set, as in this case ImageNet. We do 40 tasks of 25 classes, and 25 tasks of 40 classes, and with a growing memory. And then we see also that in this case, BIC and IL2M, so two bias correction methods, do very well. And surprisingly, in this case, iCarl also does very well, which for the analysis that we have seen, it seems to be correlated with what we said before. If the first task has a good representation, this method does a lot better. In conclusion, we would say that for regularization-based approach, distillation is better if you don't have exemplars. But if you have exemplars, then fine-tuning actually outperforms quite a few existing methods, and therefore is a baseline that has to be taken into account in the future. Bias correction at the moment are the ones that are performing better. And then taking into account that a larger first task or a good initialization can benefit some methods more than others, like Lucid and iCarl are a great example of methods that perform better when they have a good initialization. And now to the final part, the metric learning for novelty and anomaly detection. So in this case, we have been talking about learning a sequence of tasks, but when we will apply these on a real cases scenario and a lot of applications, what would maybe happen is that we are able to identify, to classify a group of classes, but when presented with something that is outside of the distribution that you have been training, then you don't know if this thing that is outside of your distribution is a novelty, is something that maybe you will be interested in learning in the future, because this is part of the continual learning group. You should be able to identify new things that it will learn next, or on the contrary, it's an anomaly or something that it's not interesting for you to learn in the future. And it's good to know that both of them are considered out of your distribution or the training distribution that you've had, but they're two different concepts, and we believe that there's a continuous representation between them where you will have things that are more novelty and then will shift towards an anomaly when you don't want to learn it. And what happens is that most of the work that we see is trained using a cross-entropy loss. And the cross-entropy loss, in the end, it's forcing the outputs to output something that looks like a 100% probability and all zeros. So it's basically training the network not only to learn the task at hand, but also to be very sure about what it says. And then it happens stuff like we see here, where we will train a network to identify traffic signs, and then you get a background patch that for some reason has got into our system, and it will say that it's a speed limit of 15 with 94% of confidence, or this one, which is more normal, that it will fail it, which is okay, there's a maximum of 15 tons with a 96% confidence. We can understand why this network would make this mistake, but this mistake should not happen. And we think that it's basically due to how the cross-entropy forces this high confidence as an output for the networks. Our solution to that is to use metric learning and then learn an embedding space. And then in this space, we can be able to be less overconfident when presented with out-of-distribution samples. And as we were saying before, we can have novelty and anomalies on the out-of-distribution. So our way of solving it is if we are able to use some data that doesn't need to be labeled, but that we know that it's out of the distribution, we can use that in the mining of pairs of the metric learning in order to tell the network where are the limits of the knowledge that it possesses. To do that, for metric learning, we use the contrastive loss, which is a staple on metric learning for many years now. And it basically proposes that whenever you get a batch of images, you can organize pairs inside this batch so that when a pair has two samples that belong to the same class, then you will try to push them together in the embedding space and form a cluster. And if the pair contains samples from different classes, then you will try to push them far apart. This makes it so that you end up having clusters of the same class on the embedding space that are separated between them. But if on top of that, we also do mining so that when one of the elements of the pair is an out of distribution, it doesn't, you don't need labels, you just need to know that it's an out of distribution, then you push it far away from the cluster of classes and push it to the border of your embedding space, then you can be more robust to out-of-distribution detection. And our motivation for that is presented by doing this simple experiment where we learn the numbers 2, 6, and 7 from MNIST handwritten numbers dataset. And what we do is we learn the three classes on cross entropy with the contrastive loss, and we also the contrastive loss with our extra mining of out of distribution, which in this case are the numbers 0, 3, 4, and 8. And what happens in here is after training, we get these spaces on the train. This is the in distribution, but then we evaluate on different types of out of distribution. So in green, we see that the numbers 5, 9, and 1, which are the numbers that are closer in some way to 2, 6, and 7, respectively, they appear to be, they will be what we will consider a novelty. It's still a number that it's very similar to what you've learned, and maybe you will want to learn it next, and it's positioned near the other ones. And if we see the anomalies occupy different spaces, and in the case of cross entropy, the anomalies can occupy spaces that are very, very close to the centers of the numbers 2, 6, and 7, while when doing contrastive loss or our mining, we obtain that there's a separation between the anomalies and the rest of the clusters that we've learned. So we did some experiments and we compared with the state of the art, and then we decided that we wanted to try with a more realistic scenario, and we proposed this Tsinghua traffic sign dataset, and we proposed these traffic signs that we see here. So on the top left is the in distribution, so it's the one that we will be learning, and they're grouped in a way that it makes sense, so all speed limits are learned and so on. And then we put seen out of distribution, the images without labels that we will be able to see during the training and treat as out of distribution. And then we will have another separate group to the previous one that is the unseen out of distribution that we can use for testing purposes. And on top of that, we have background patches from the Tsinghua dataset and Gaussian noise, basically. If we do that, if you see as you can see on the left, we can very easily learn an embedding space that separates completely each of the classes. And then if we look to the right, we see that the novel samples that have not been seen, that are traffic signs but are not belonging to the classes that we've learned, occupy a part of the space that it's in its majority it's close to the clusters, but it's not overlapping with the clusters majorly. It's even a bit better than here because, of course, this is an embedding that it's quite large and this is a TSNE representation, but numerically we see in these results that that's the case. So the numerical results compared with Odin, which is one of the state-of-the-art methods at the moment we were researching this, is that if we are doing only the contrastive loss, so we are not applying the mining that we propose, just changing from using cross entropy, and in the case of Odin, it's cross entropy, but also an input preprocessing and temperature scaling. If we compare it with the contrastive loss, we already see that the performance is better in our case. In these results, lower is better. It means that the error is lower. And also, it's interesting to see that if we will use our our mining, then depending on the data that we're using as out of distribution, then we get different results, which were quite interesting because we can see here that if we, of course, use Tsinghua images, then the performance does even better because we are able to get samples closer in the embedding and put a limit to them, let's say. But if we use Gaussian noise, we get better results than if we use background patches, which is quite interesting. All in all, we propose a metric learning algorithm that is comparable or better in the scenarios that we present to the state of the art. We propose to use an embedding space, which seems to be better for the problem that we've described. And it allows for a continuous representation between novelty and anomaly. We also propose the new scenario or benchmark on the traffic sign recognition. Finally, in conclusion, for the first part, we have proposed a new approach that takes into account the activation statistics when doing compression for domain adaptation, and it's capable of compressing up to a 5% of the original size of the layers without a significant drop in performance in the experiments post. We moved also on to continual learning without any forgetting, so we propose a method that is capable to do zero forgetting based on ternary masks, and we are capable of beating the state of the art in some benchmarks. And then regarding class incremental learning, we do an extensive analysis, which was I think, very timely, given that the race on class incremental learning has been very interesting lately. And we describe the challenges, the methods, and the scenarios for class incremental learning and compare on a framework with 12 state-of-the-art methods and some baselines. And then in the last part that I just described, we did detection of out-of-distribution based on metric learning and propose a new benchmark with the Tsinghua traffic sign dataset. And the work of this PhD has resulted in several publications, here listed in chronological order, that I've been able to do with collaborations with multiple people. So thanks for listening, and I would also like to thank my supervisors, Joost and Andy, because their guidance throughout this thesis has helped me get the results I've got and become a researcher. So now I guess I'm ready for the questions.
Okay, very good. I think we can start with either Herman or them. Who wants to start?
Herman, would you like to start? Actually, sorry, go ahead.
Is it working with the audio, or is it you're listening twice? Because else I will also put the headphones. When you talk, does everybody hear it properly? Okay. Okay.
Herman, would you like to start? I guess.
You're muted.
Hi.
Yeah, sorry. Yeah, sure. Let me start. First of all, by saying, very interesting topics, Marc, you have, I guess, addressed in this thesis. I think that these four topics are very related and very interesting. I think, as you mentioned, they have been, let's say, very incrementally said by the community and so on. So, in particular, like lifelong learning and so. In terms of, if we talk about the first part, right? So the compression part, and so on. I think you mentioned about you were talking about the your method as kind of a lossless compression method, and I think that is very interesting. And in general, if we kind of conceptually combine compression and continual learning, right? So if we think about an approach that learns continually and tries to kind of mitigate catastrophic forgetting, so that's something that we don't want to have for sure. And then on the other side, we have like the possibility, let's say, of compressed network to make sure that we reduce the number of parameters and so on, just to keep consolidated knowledge, so without having significant loss in knowledge and therefore in accuracy. Of course, at the same time, I think that since you will anyway encounter computational and memory limitations at some point, we know that to some extent a kind of small degree of forgetting might be desired, right? So this is something we can refer to as graceful forgetting, which is the opposite of catastrophic. So I think that it's a very interesting problem. So do you think that these compression approach that you're proposing and so on can also be seen as a mechanism to drive or modulate graceful forgetting in a specific context? So you do have kind of a loosey compression. So can you elaborate on your thoughts about how that compression mechanism can be related to having a more like graceful forgetting mechanism?
Yeah, sure. Thanks for the question. Actually, it is kind of connected, because when we started the thesis, we were already thinking like the compression came after we did my master thesis, and we were also thinking of how can we learn hundreds of classes, right? And one of the things that was coming on is like, okay, you can learn a lot of classes, and then the compression comes that if you have a continual learning system that is learning a lot of tasks, then maybe you will want at some point to be able to have this macro network that is capable to do a lot of things very well. But if you want to deploy that into your mobile phone, then specifically thinking more on task incremental learning, which sometimes now it's looked down as, oh, it's not important, but I think it is, because if you will have something that it's capable to do a lot of things, then if you know that in your phone you need a specific thing for solving the task of dogs or whatever, then you could apply compression in order to transfer the knowledge that you have, the general one, and specifically look at it loosely biologically or with a biologically relatedness. Is like, okay, you can know a lot of things, but when you're doing a task, you probably are only using those connections that are related to it, right? So being able to compress, it's interesting in this case. And as you say, since we already noticed that sometimes compressing from learning on a larger amount of data, which can be distracting, let's say, then actually eliminates a bit that noise. The accuracy go a bit up even. So I think this is a bit the connection that I see on it.
Cool. Yeah, because at the same time when you might be running your network and so on, you might improve, I guess, your accuracy on the, let's say, test. You are kind of forcing the network to generalize more instead of overfitting and so on. So
Also, I think like graceful forgetting is also interesting, I guess, in the cases where you are also doing continual learning, but there's things that you actually don't need. Like if I'm learning to identify cars, I will do it, I will learn new cars every year as new models come, but after 30 years, the cars that are 30 years old, I can gracefully forget, and how many samples will you get of that at some point, right? Like if we are thinking of a very lifelong learning, like then this is the case. So I think this is what connects a bit more maybe with the graceful forgetting.
Yeah, and for sure I think graceful forgetting is something very interesting, because you may want to forget, like maybe, the brain test, like you may want to forget specific, episodic events, but anyway, remember a class, right? So if you're learning cars, you don't have to remember a single class.
True.
Cool. I don't know if I can move on with another question, or actually we have another person asking of it, which is, what is your...
I would say you can continue and put all questions, and then we switch to another one.
Sounds good. So now we're talking about the class incremental learning, and which again is a very interesting problem for sure. It's a really interesting problem for me. So you mentioned at some point that the approaches kind of benefit from having like initial tasks, right? So that performance looks better when there's initial tasks, and that makes me think of some studies that are out there about critical periods of learning in deep neural networks. Again, this kind of has an analogy with what's going on in the brain, in terms of that we know that the brain, there's a lot of studies supporting like the importance of critical periods of learning, right? So that's something that actually bootstrap more efficient learning in subsequent steps. So can you actually elaborate more on why you think that's the case, that having having initial tasks actually benefits the performance of these networks as you then start presenting subsequent tests?
Yeah, for sure. That's a very interesting question, because so for me, I think that this notion appears a bit more because there was some corpus of work that I've been seeing a bit less maybe in the circles of this article that we were discussing for the survey, for example, but it was like curriculum learning, right? And curriculum learning was already pointing out these connections also sometimes with some biological studies on how learning happens, right? And of course, neural networks are not brains. But this is where sometimes these loose connections for me make sense, or this is the explanation at which I arrived, because when I tried those experiments, we were seeing a consistent improvement in a lot of those methods when the starting embedded space of the first task was better. That said, I would also say that I could be wrong, and maybe just like way that these methods are implemented, like they are benefiting specifically from that, like a bit like the method I proposed for ternary masks. It makes sense that it will benefit from it, for example, right? Because you will be using those connections in every single task that you will learn afterwards. But I think this is the reason why I think connecting to curriculum learning, the order in which you learn things is important. And in this case, we will not be talking so much about the order, but about being able to learn a task when certain concepts are, or filters in this case, are available. I think it should make it easier. No, that's. I don't know if that answers your question or.
Yeah, no, I think interesting points. I guess for sure, like in terms of without going into the biology and biological aspects, which I think are really interesting and but yeah, you made some.
So in terms of implementation, I would say, because I mean, if your embeddings are robust already, are capable to do more things, then of course when you're learning a new task, you would be able to reuse them without need to modification, right? So if they are more robust, then you will probably be able to use them as is, and you will need very little more to do them. While if you are lacking in, let's say, something, it's not as easy to already have some filters that you're using and that you've overfitted in some way too, to like the learning of merging filters to have the same concept in order to stay in the capacity that you are limited to. I think it's what introduces catastrophic forgetting in a much more easier way than if you can reuse some very strong filters from your base, like the knowledge that you've already had. I think this is something that it's very clear when at the beginning all the weight-based methods were trying to force those weights that are very important for having those filters not moving at all, and that's what was allowing them, so in the direction of more machine learning. That would be my answer, I would say.
Cool, thank you. And always staying in the framework of incremental class learning and so on, you mentioned one of the phenomena in which neural networks may tend to remember the last seen class more, right? So if you're learning ABC, and C is the last kind of batch of stimuli to be shown to the neural network, that's the one that will probably be more remembered. And there's going to be different degrees of forgetting from the previous one. So that also may depend, in whether classes have like balanced number of samples, and may also depend, I think, on the order of presentation. So I wanted to ask if you're in your empirical studies in incremental class learning, you have, let's say, extrapolated any key learnings about how imbalanced data and the order of presentation actually influences accuracy of incremental learning of classes.
Yeah, I mean, we had this. You can still see the slide, I mean?
Yeah, I can.
Okay, so in the thesis we also showed this this graph, which was showing that this is iCarl on Cypher 100, 5 tasks, and then what happens is whenever you're learning the new task, since you are able to, you are looking at all of the outputs, but you have unbalanced data, then it's a bit the same. Your cross entropy is really pushing all the time that there will be a 1 on the new classes, while zeros on the rest. So if we will only train for one epoch, the most optimal solution in the solution space is to randomly guess from the new task. because all of the data that you're seeing, it's basically all of the data from the new task plus a few exemplars of the previous ones. So during the first moments of training, I assume that what happens is that, like, the way to reduce, if you have 1,000 classes but the new task is only 20, then you go from 1 divided by 1,000 chance, let's say, to 1 divided by 20 just by guessing in the newest task. So if you make the magnitude of the biases and the weights a bit larger, you will make it so that those activations that are benefiting just the new classes will be firing higher, then you will get more guesses, at least by chance, on the new task. And I don't know if that's what you were meaning, or?
Yeah. I just want to discuss around, what are the effects of, imbalanced data and order of presentation, and do you think that, for example, like memory replay or rehearsal, like depending on how you want to do it, is kind of a viable mechanism to address like the effects of imbalanced data, right? So you think about, let's say that you have 3 classes and they'll have different number of samples. Like, can you think of, again, like memory replay or data rehearsal as a way to address these imbalance in the data while you're training your network?
Yeah, well, this is the question, right? Like, I would say a few things why, like, the problem for me is there's a few things that are, like, bother me when we think about exemplars and so on, which it's why I don't know if it's the best solution or not. If we're talking of this kind of, like, class incremental learning or task incremental learning where there's a sequence, I think it's different. I'm skipping, let's say, online learning where I would say it's a different setting. But for this one, already connecting it also with the previous question, like EIL does balancing, and this helps, but this already doesn't necessarily show that it fixes this task recency bias. So regarding exemplars, the problem for me is that, one, I would think that moving into metric learning for class incremental learning, so using embeddings and learning the embeddings, in my opinion, is much more interesting. And it allows you to create an output space that you can do more things on than just using a cross-entropy loss, I would say. And this is interesting because when you do that, then you can think of, like, okay, we are trying to balance the number of exemplars that we keep because it's this way the representation is the same and there's no, but then you look at the results and herding is barely winning random selection half of the time. So this is the part of me that I usually tend to think that choosing the correct samples, it doesn't matter the number that much, but if you have a car, maybe you will need more samples because there's more angles that you can see it from, and then if you're looking at a football, then you will need less, I don't know, in a broad way. Yeah? And the problem with exemplars is that the ways that we do it now, we try to solve it, I think, in these ways that I'm not completely sure that it's the best. While in metric learning, maybe learning the prototypes of the classes, right, in an embedding space and being able to put classes together will be better. The problem for me is that when you have an embedding space that has already been learned and then you bring a new class and it has to squish inside the middle of other classes, that can create so many problems that that it also has its own chimeras to beat, let's say. Because in my experience with metric learning, it has a lot of potential, but it usually has lower accuracy, at least, or performance a lot of the times. Like it's not so easy to train. Like it has its own problems. So my opinion on exemplars is a bit in this direction, where I'm not sure if it could not be done in another way, rehearsal. I think maybe instead of data, it should be at some embedding layer. I think some of the papers that were trying to do things with that were also giving quite nice results, even if they were not beating everybody else or whatever. But I would say that's my stance on this.
So yeah, so from replaying, like, please see, yeah, so from replaying explicit data to actually maybe replaying latent representations of the input. Yeah, my last question for now. So I think I also want to talk about the novelty and anomaly detection part.
Sure.
It's also pretty interesting. And in particular, I'm kind of interested in the relation between novelty / anomaly detection and continual learning, right? Incremental learning. So I think there's a strong connection between, how much, the amount of learning that you have based on how much learning you think. I mean, you mentioned the fact that if you have a complex object, you may have, let's say a longer sequence because you have to learn it from different views, different angles, and so on.
Yeah.
Whereas if you have kind of a sphere and so on, it's pretty straightforward. I'm thinking of this scenario in which you have for example, a robot that is interacting with objects and choosing what to learn based on the complexity. So, do you have any thoughts in how novelty / anomaly detection can be used to drive or modulate the amount of learning you have in a continual learning framework? Since that always keeping in mind that we will always have limitations in computations and memory. You have algorithms that are more about regularizations. Like once you translated knowledge, you just leave it there. You don't want to attach those representations anymore. And then you have other methods that actually just keep updating, in which you may have some forgetting. So my question here is again, how would you use this framework, this concept of novelty and anomaly detection to actually maybe modulate the amount of learning you have in different parts of your network?
Yeah, it's interesting. Actually, we are working a bit on that. So this is future work that let's hope that I can share at some point.
You can't tell me, I gotta wait.
Yeah, no, but the issue is that we were like, it's not so much in the direction that you were saying. I find what you propose very interesting. I guess that it's also very interesting for you because it's more like, for me, the relation with robotics, which is what I think you work more on, right? Like more like these sequences. I think something that could be interesting is, in these cases, if you would have a robot, I don't know if it's the scenario you're saying, but imagine that you will have a robot and you want to learn continually in a scenario where you will do these experiments where you give the hand robot, right, that has to learn how to grab objects, you give it a bucket of objects. It will be interesting to see if there's some kind of active learning, which is kind of connected also to these things, to be able to identify which is the next task, given your representations, that will be better to learn. And this is a connection for me on active learning. It's also a bit like when you move from active learning of knowing which data you have to label in these robotic scenarios. For me, it's like moving to curriculum learning a bit, as I was saying, like, which is the next object that makes sense? If I look at this bucket of objects, I should see that the sphere is closer because I've already learned how to grab a dumbbell. I don't know, like, the example is not the best maybe, but I think you get the point. So in here, I would say that this is where a bit this line of novelty anomaly would be a continuum that you could also use as an active learning way, where you will want to be able to order these novelties in a way that you can learn them in the more efficient way, maybe. I don't know if there's any work in robotics specifically that is already going in this, but this is how I would connect the novelty anomaly, let's say, continuum space that we propose with continual learning. I think it might be tricky when you start from scratch. I think this is something that makes a bit more sense when you've already learned some classes or some objects, and then you do the last thing. And that's why I will connect again. This is my intuition, because I believe that having a first initial task that it's good and has a robust embedding has a better, especially in real scenarios, I think. Like theoretically, maybe, who knows, you do MNIST or, like you can get very good results there on almost everything. So.
Yeah, no, excellent considerations, and in fact, active learning was where I wanted to go. So, great. Yeah, at this point, I'd like to hand it over to the rest of the committee, because I don't take all the time. So thanks a lot for your answers.
Thanks for the questions.
Thank you.
So, Vodka?
Yeah, thank you very much, John. Marc, first of all, congratulations for the presentation.
Thank you.
I also want to congratulate your supervisor for your work. I enjoyed a lot reading the thesis. I have the feeling it's very clearly written. The contributions are very clearly highlighted and very well structured at the same time. I like that all results are supported by a good publication record, and each chapter is accompanied by an exhaustive state-of-the-art review. I like that the novel idea and concepts you introduced are very well described, and almost everywhere there are detailed graphics which support them, which add more clarity to the presentation. And finally, I also like that the results you present are always carefully analyzed, and then interpretation is always provided. In particular, I was really impressed by the work in chapter 4 about class incremental learning. I acknowledge it should have been a huge amount of effort.
Yeah.
But at the same time, I think this is the first time I find this exhaustive analysis of so many algorithms, of so many architectures and data sets. So besides these general considerations about your thesis, I have some specific questions, and I would like to start with chapter 2. So when you were talking about layer factorization, you refer in your thesis about the fully connected layers. Did you think to apply a similar approach to the convolutional layers?
Yeah, first, thanks for the nice words. I mean, thank you. Yeah, for sure. We tried for some time to make an extension. The main issue about it is that we were, the way that we formulated that was working very well for fully connected layers. And the problem is, I think it's not only on convolutional layers, it's the fact that at the same time as this publication came out, all of these residual block networks were getting a lot of attention. And residual block networks have much less parameters than the other ones. And the way that they structure these 3x3 filters and so on, it made it very difficult to be able to apply the method and let's say, compress in the same way. It's not as easy to be able to do a decomposition and, let's say, a merging of some of the filters when you're on the fully connected layer, but when you move in the convolutional layer, you're doing the same thing on the filters, which have to keep their height and width dimension, like the spatial dimensions. So at some point, we dropped it because it was like all of these methods that were doing more like efficient layer, were getting very huge gains. And we didn't think that we would be able to achieve results in enough time. And we also were starting other projects. So that's basically the reason. But I would say the main limitation for that was the fact that the residual blocks, which were getting so common, are much trickier to compress, and even with SBD or like already others, or prune even. So it was actually, there was these NIPS, there was a NIPS, NeurIPS talk that was saying that these 152 residual networks, it was better to just prune blocks, residual blocks instead of anything else. And then they were pruning the blocks, and that was working better. And our method cannot work with removing full block, let's say, or not in the same way. It will be a completely different setting.
Okay, thank you. Now, do you have the thesis at hand?
Yeah.
I would like to ask you to go to table 2.4 on page 22.
Yes. Yeah, table 2.4.
Yeah, I think here that both in the case of compression of fully connected layer 6 and fully connected layer 7, so you have, even if you have a very strong compression from 1024 units to 32, in the case of your approach, the accuracy is only using 4 or 5%. Could you please explain a little bit how it's possible to obtain such a high rate of compression?
Yeah.
Without losing accuracy, basically, I mean, or losing a very small amount of accuracy.
Yeah, the thing is, in the specific case of the birds dataset, I think there's already a few classes of birds that are learned on the ImageNet dataset. So I think this is the reason why there's ImageNet was already, since we are initializing the network from a pre-trained model, I assume that there was already maybe I can show in the slides. So this one here. So if you look at this graph, both birds and flowers have a very narrow tail, flat tail. Yeah. I think that it's already the representations that have been learned are already very good for learning birds and are not necessarily occupying all of the embedding space. They're probably limited to a few dimensions. That's why we can reduce so much and have such a large compression in this specific case. It's also quite noticeable in flowers why when you move to actions, you see that the drop starts to be a bit more significant. Because flowers and birds are more related to a lot of the classes that were learned on ImageNet, while actions is something that it's not so relatable.
Okay, thank you. Now, could you please go to table 2.9 on page 25?
Mm-hmm. Yeah.
Could you explain a little bit this table, because I also seen that if you apply compression, for instance, in the upper part of the table, you even get better results than using no compression.
Yeah.
Could you explain a little bit this table?
Yeah. I will try to maybe use a different concept that when I was doing in the presentation. So the notion of it, as I understand it, is that whenever you train a network, when you're trying to learn a data set on a network, then you use the capacity of the model that you have. But that capacity will be always above or below what you will optimally need, let's say. In the case of learning Mock Pascal on the faster CNN, I think that what happens is that there's some, let's say if it's over, in the case that it's the capacity is of the network is larger than what you will optimally need to learn Pascal, what happens with the network is that there will be filters or groups of filters that will be firing at the same time, or groups of them that will be firing at the same time, right? Like there will be not that useful, and those filters can introduce some noise when training. Like if we are trying to compress, maybe those filters that were learned on the ImageNet and then relearned on Pascal, that maybe are introducing some kind of extra magnitudes on the outputs, but you remove them, then what's happening is you're kind of removing the noise, and that's why you get this light boost. We never saw, though, that this gain was bigger than 1 to 3%, maybe, like it's, you will, I don't think you are, I don't know, I would never say never, but intuitively I would say I don't think that it can be something that improves the performance. It's a side product that can happen when, let's say, you have an ImageNet that has been learned on birds, and then the capacity is 12 or 20 times bigger than what you need. You can learn birds also with a similar, in a much, much smaller network. So then the filters are maybe repeated, and some of them become not that useful as it seems, but you need to learn them. So yeah. This is the intuition behind it.
Okay, thank you. Now, moving to chapter 3, I'd like to start with a question for regarding the title. So, do you think that any forgetting is a desirable property for a real-world lifelong learning system?
Yeah, that's a very good question. And there's two things. Where, like, Vincenzo Lomonaco was being an international evaluator for this thesis, and he said he referred to all of these as zero forgetting instead of any forgetting. And I love the term, so I would say from now on, I would say zero forgetting. But zero forgetting is very desirable for a lot of applications, I would say. I mean, if you will have a system that already works and you have it, like it's capable of identifying a certain number of things, like there are several reasons why you would maybe want to have zero forgetting. It could be one, because you have that system that works and you are trying to test how new features will do without compromising the previous features. Then you can do a zero forgetting learning, see how the new features are doing, and then once you have figured out how to merge them together or something, then you can do it in the other way. But I could imagine also that depending on which things you're doing that are very critical, I don't know, I mean, what about medical imaging, right? Like if you have something that works, you don't want to risk it. The main problem with catastrophic forgetting, or forgetting in general, it's not that it's catastrophic only. It's the problem is that it's not quantizable or easily quantizable. When you decide to learn a new task, if you're not doing zero forgetting, which is a separate thing, then you don't have any insight on what will happen. Like you would do it, but then later you might have a lot of forgetting, right? So if you don't want to take that risk because it's a specific task that needs that, then I would say zero forgetting is still interesting.
Yeah, my question was motivated by the fact that of course, I agree with you that sometimes it depends on the application, but also I think that in some real world scenarios, you have some limitation of resources. So imagine a system that runs on the self-driving car, on a robot, so
for sure.
Resources are limited.
Yeah.
So achieving no forgetting using a limited architecture, a limited resource, I think it's very difficult to do it in practice.
I agree completely, but I have the feeling that if we're talking about self-driving cars, this is something that is extremely important, that things are correct. So in those applications, I don't know how much, like I don't know if I would have to think the situation where I wouldn't want something that is zero forgetting. Like imagine you having cars that you have already given to your clients, and then you patch and update, and you have no idea, like if you allow zero forgetting, you're guaranteed that maybe you will do bad on the new feature, but the previous features will be exactly as they were. This is, in a lot of scenarios, desirable. What's not desirable is to send an update to all of your cars with a new thing where there's a possibility of any forgetting at all. And it doesn't matter. There's, some hills in some country where the shape of the mountains specifically generates this forgetting, and then the speed limit is changed to something else or whatever, and you're done, right? Like this is specifically a case where I would say zero forgetting is highly desirable, in my opinion.
Okay. Now let's move to a more down to earth case, and concrete. I refer to the. Let's go to figure 3.4 on page 43.
Yes.
Okay, so regarding with this architecture, you have some comments on the next page, where you say, okay, so we start with a certain number of nodes per task, then we add task 2, then we increase, we allocate to this new task another number of nodes, but my is very specific to this case. But I was wondering, have you thought of more general policy expanding the network architecture when a new task is presented?
Yeah, that's a very good question. We present this is that there's a balance between trying to be able to compare in a fair way with previous state of the art, which would be that we have to limit our model to not growing past the size that the other models or the other methods are using, such as HAT or PACnet, because then it will. We considered it would be unfair. Yeah, I mean we have 50% more network just because we have explicitly explained how to grow it, right? So we decided on this more strict way of partitioning how much we can add per task to show that even limiting because this is limiting our method. All of the results on this paper are limiting our method. Our method is capable to expand more than it is. But then if we are talking about overhead, it will also be a bit, I don't know, hypocritical to talk about overhead and then say we can grow as much as we want. No. There's two factors that are important here. One is we did notice that when you grow, it tends to grow less and less over time as more representations are learned. So in order to define more when it will stop. And yeah, I would say that we decided to focus on being able to limit the network to be comparable with the other state of the art, than explain the strategy that you could use for growing, because this is highly related, and this is connected a bit with what Germán was asking before with active learning, testing how much the network has to grow, like the minimum amount that the network has to grow in order to better solve the task, reminds me a bit of these kind of problems, right? Like where you don't want to try all of the options, let's say, so you want to propose. The one that we propose, I think it's okay. It's we allow at every task to grow as much as needed up until the limit that we've set. So some experiments are fixed because we thought, okay, let's fix it. But the ones that are not fixed, which are most of them, then when you learn the first task, you have you try different percentage of the network, and then you choose one that it's good enough compared to the maximum that you will achieve, and then you move on. And then when you run out of space, you run out of space. Like if you have to learn the next task only with the head, then you learn it. But the thing is, we didn't have to worry about that because there was always a bit of space at least. I think the actions data set was the one that was a bit trickier because the last tasks are a bit more difficult to learn with fewer samples, if I remember. I'm not 100% sure, but I think that was the case. And then, of course, definition of a better growing strategy would be, but I think given the limitations that we propose, the growing strategy works perfectly fine and provides results that are competitive enough. So, yeah. In future work, we can explore it. I mean, this is already an article that it's still under review, so this is perfectly good food for thoughts for how to improve it in later stages. So, yeah.
Okay. And the last question regarding this chapter, so related with this strategy of expanding the network architecture, could we say that because of the particularity of your approach, when adding a new task, the training time to incorporate this new task is constant?
It depends. It's quite constant in the tiny ImageNet, but I think this is in the random split, but I think this is just, I think it depends on the task that you're learning. Like, in general, it's not difficult to learn, though. I would say not based on the ImageNet results. Like the task on the ImageNet experiment, each task had a very variable amount of epochs, which was not necessarily related to the amount of memory that we were adding. There was no correlation between the two of them. Because I also checked one time and I was so clear that it was not that, and when looking the other experiments, it was clear that it was not. Maybe there is, I mean, some kind, but I have the feeling that it also depends on finding this perfect capacity spot, let's say, probably. But I would say not. I would say each task has a variable amount of.
Yeah, okay, so it's of course task dependent, but because depending perhaps on the number of classes you have each task, but assuming that each task have the same number of classes, I think it should be more or less.
It's comparable in the sense that in broad numbers they are comparable. But if I look specifically, there's a variability there. I would say that one of the things that I noticed is that, for example, our proposed method and HAT are a bit faster to train than some of the others, like BACnet. BACnet, of course, because there's an extra step of compression and so on. But I think the fact that we kind of limit in some way the activations that can be backpropagated limits the capacity, so the task has to learn on that space that is given. And in the end, HAT also does something similar because the sigmoid functions are that are easier to learn are the ones that look more like step function, at least in my experience. Maybe Johan can give more insight on that. But if you keep the sigmoids high with a S max of 400 or 800 or something like that, like the larger side of the values, then they train relatively fast, while in methods that are doing like BACnet or whatever, it takes a bit longer, even if the capacity is somewhat relatable, let's say, because they also limit which ones you can change. But the way that they do it, I think it's affecting it.
Yeah. Okay, so now moving to chapter 4, I think German asked a lot of questions regarding this chapter, so I'll be brief.
Sure. Sorry.
Do you think that the order in which you present the tasks in class incremental learning has an influence on the outcome, on the network performance, on
Yeah.
classification accuracy?
Yes. It depends on some details of the scenario, but in general, yes. There's like especially if the tasks are not random, like you get a data set and you randomly split it, then usually not so much. But if the splits have some semantic value, then for sure. And actually, we have a workshop that we published. Let me grab it for you, just a second. This one here, number 17, that we were talking on exactly class orderings. I've lost it. And here we show, for example, that in the case when you're taking random orders, then it's different. But you can see that if you order the tasks from harder to easier or the other way around, then there's some difference. It's I said sometimes because in general I would say that's my argument for most cases, but I have to say that the experiments we showed in here for Psi400 showed that Psi400 actually is a bit more robust, let's say, in which ordering you choose. Like the curves are slightly different on where the forgetting happens, but the actual performance is. Yeah. So yeah.
And what I want to mention about this chapter 4, I like in particular the discussion you provided in the section 4.7. I think it's very insightful because you give a lot of potential directions for future work in class incremental learning. So,
yeah. Thanks.
I a lot, and from this list of possible direction, what I think in particular it will be more and more relevant in the near future. It will be the self-supervised learning, because it's inherent to have more and more unlabeled data, and for a real-time system that has to run on the fly, so there is no possibility to manually provide labels for data. So,
I agree completely, and actually this is related to the discussion we had before with Germán, right? Where continual learning, if you have unlabeled data, then having some kind of out of distribution detection that can tell you which are the novelties without needing, like without having labeled them yet, just knowing this is something that looks like you would want to learn it, but you have not labeled, then becomes more valuable in the loop of continually learning. Yes.
And
Thanks.
I have also a short question. You mentioned at some point about parameterized exemplars. Can you say 2 words about what parameterized exemplars are?
Where do we mention that? I don't remember right now.
It's section 4.7, I think. If I'm wrong.
Do you see, or can you point me to the part or something? I mean, without the context, I'm not sure about it.
Yeah,
we need Control F for our eyes when reading physically.
Like mnemonics, Marc.
Okay, but this is what mnemonics propose. I would say parameterize or any way that we would store exemplars in a way that it's not storing the data, but storing the representation or some other kind of representation of it. It's also connected to what we were saying before, that I consider that it's more interesting than storing the exemplars per se. Yeah.
Oh.
Like, yeah.
Thank you very much. And now finally moving to chapter 5, I have one question here. I could understood that you, using the same strategy, you could distinguish between novelty detection and anomaly. But is your method able to distinguish between different novel classes?
No, no, that's not the objective.
Considered as novelty.
Well, I would not say a rotten no. Like the method is not designed for that. It's designed for detecting. It's in the end, it's out of distribution detection. So the problem that we try to solve in the experimental scenarios are knowing if something is inside or out of the distribution that you want to perform on. And I would say in general, no. But if your embedding space that you're learning is rich enough and good enough, like you learn it over time or on a large amount of classes, and it's well, like the dimensions are really having meanings maybe on the last layers, especially on concepts, then I would say maybe yes, because you would be able to see that something is outside of the distribution. But if you're detecting traffic signs, and then you get 2 new traffic signs that are a novelty, if the embedding space is rich enough, you should be able to see that those novelties are taking space out of the distribution, but in a separate space, so that they are easily absorbable via another round of learning, hopefully. Because on the new traffic sign already has a red circle, so you can use that, like that knowledge, and the other one has a blue square. So those should appear in different parts of the space if there's characteristics that are already coded for detecting color and shape, let's say. So I would say no in general, but yes, it's a potential. And you could encourage it probably in some way, I think.
Okay, thank you very much, Marc, for all the answers. I have no more questions, and congratulations again for the...
You're welcome, and thank you for your questions.
Now it may be my turn, okay?
One left.
I had written
quite some questions. A couple of them have already been asked by the other members of the jury, so let's work for me. First of all, let's start with the compression part.
Okay.
I also played a bit with compression in the past, and
I never liked the way of reporting these compression breakers. Like when people does these things like pruning, okay, we can prune 99% of the weight in our network.
Yeah.
But then, and I don't like it because it's mostly dependent on the data and on the architecture. So, which are your thoughts on that, or how could we improve this situation? Because I mean, you see the typical result, right? So we prune this BTG network in MNIST to 1% of the weights, and then you think you are encouraged. You think, wow, that's great. No, let's try it with my complicated audio data set. And then it turns out that you cannot go beyond 5% less weight than the ones you had. I mean, it's quite annoying to find all these all the time.
That's a good question, and my answer is not for falling on your side, but I hate it too. Because I think that the problem is it's not only like compression and the percentages, it's also like I will report flops, I will report on memory, I will report on, like there's so many, and in some papers, I don't know if it's me or it's the way it's written, but sometimes it's not so easily, even if they give you the result, it's not so easily to see which one they are appealing to, right? Like we were hopefully showing that we were going for memory. Like we wanted to reduce the number of parameters, and that's why in all our graphs we are talking about percentage of parameters. We didn't want to tackle other things because if you look at the branch of related work that is like quantization, we cannot compete with that, right? Like this is a completely different hydra. But they can be combined, so it makes sense to say, okay, we're reducing the number of parameters already from the start. Maybe if you apply quantization to it, then you can add other benefits like the number of flops or like the execution time. If you reduce floating to some of these binary weight, mass, or stuff like that. So I agree, and I understand the feeling that sometimes it's difficult. I think it's a bit unavoidable to some extent because we are putting network compression as a name to all of these related work that I was showing earlier that are like, those are the 4 branches that more or less I would point, but new have appeared also. So, and if you go in each of them, I have the feeling that different metrics are more relevant, while if you use metrics from the others on the incorrect one, it's not sure that it will do. I don't know. I would say also that we tested this on this medical imaging case, so I would like to say that at least in that case we were seeing that we could lower the frame rate so that it could be video. Like it was just improving these milliseconds so that it will be able to run in a continuous loop. So at least experimentally we were able to see that it has a benefit, but I agree with that metrics.
Also on the practical side, which is your experience or what you do afterwards. So let's say you have this network, you are able to prune it, but then how do you really implement it? Or
That's I would say the major drawback is
connected layer. Okay, I mean it's just smaller matrix multiplication and that's okay. But if you go towards more elaborated pruning strategies or other strategies, I mean, how do you really implement it to get benefit of this of operation? Let's say.
Yeah, that's a good question. I don't know if it's exactly what you're asking, but the way I understand it is, I don't know if you're familiar with another work we published called Rotated EWC. Okay, so Rotated EWC also had a bit the idea that we were having on this ICCV, on the compression one. And what we do in that one is when doing the training session, we decompose the weight matrix into the 3 or 2 parts. Then we learn in that. But once we're done learning and we're taking advantage of, in this case, of the representations that we wanted, then we merge them again before. So we return the network, we expand the network, but then we return it back to its original state. So I would say that in some of these cases, I don't know if, like the way I envisioned this system was that one of the main contributions from that article is the fact that we don't need this retraining that most of the methods that are comparable were doing. We fine-tuning and that's it, nothing else. So this is important because you could have what we were saying before, like a huge network that is capable to do a lot of tasks, and you can have that as, let's say, your company secret, and then you would be able to generate these compressed versions and implement it in the specific way that is needed for each of those tasks so that they can benefit from the main goal, but applied specifically. And then it depends on the architecture you're going for, right? Like if you need something that needs to run faster, maybe you will be able to use something else, or I don't know. Like this is the way I would consider it, but it's not trivial. I agree. Like it's complex.
So another question on compression. You used the activation statistics to derive your method, and I was wondering if you could combine activation statistics with weight magnitudes, let's say, or with other existing approaches, or how would these activation statistics interact with other compression approaches?
I think
like weight pruning or maybe even distillation. I'm just elucubrating a bit, but
yeah, I've thought about this, but the problem for me is that I have the feeling that the compression is like a step that you have to do. And even when we were doing this, let's do 2 fully connected at the same time, so that when you do a little bit of each, they kind of also correct or compensate in some way, because you want in the end your.
That was another question. Do you do it independently per layer, or you first start with the lowest layer?
For that specific experiment, it's we compress a little bit on both of them. The one that has the lower error, we keep that, and then we do the same for both of them. But making the modifications depending on which one introduces the least error. In this case, if we have two fully connected layers, they will just grow. And it's also interesting how to see that fully connected layer is basically chosen all the time because it has 10 times more parameters, and then at some point they start to play along. But the fully connected 7 seems to be able to recover the previous one more than the other way around, which I guess intuitively also makes sense.
Also, since you look at activation statistics, did you observe any change by using dropout, for instance, at the output of the layer? Because then the layer is trained with a lot of zeros in the output.
The dropout is used during the training, but not during when we do the compression. So we don't, it doesn't affect.
The fact that the network has been trained with dropout, does it help or is it?
I would say yes, but my answer, I would not claim that it's something related to my method. What happened when we were working on this is that usually we were using AlexNet, or BGG, sorry. And the thing is, when you use dropout, you'll get better performance overall. So we were choosing to apply compression to the models we were training that were using dropout just because the performance, right? Like if we're showing flower 70%, then we are there.
Plain performance before.
Yes. But also I think it's easily defendable because if you're applying these, you will always choose, right? Like you will always choose the better performance to compress on and not the other one. So this was a bit the idea behind it. We wanted to treat the fine-tuning step as something that was trying to guess the best performance, and then we do the compression.
I was just thinking if that.
I'm sure it helped though, like, but I'm sure, I mean, intuitively, I think yes.
Also in HAT, we were using an L1 regularization on the applications,
Yeah.
so these type of things may.
Yeah. Definitely, at least with some of the other tests, I've also noticed these things. Yes. But yeah.
Moving to HAT.
Yep. Oh no.
I love table 302 where you put, and that was our main, you need to look at it, that was our main motivation to use activation masks and not weight masks. The fact that it's way less number of parameters.
The activation weight table, yeah.
Just plain information, but people doesn't seem to realize that.
Yeah, I think it was one of those things that at some point we were discussing how important it is, I guess, and then we put the numbers together. It was like, this has to go in the in the article. It's so obvious that, yeah.
And so, I love this approach of tackling the activations instead of the weights. But now I'm working with audio a lot. And with audio, you have signals that have different lengths all the time. And then I've been wondering from time to time, how would I apply this type of activation-based approaches to an audio signal that can have lengths between tens of tokens or a language signal or something like that. That you cannot, many times you cannot just take a batch. So you need to process the signal independently of the length. You can do it with an RNN or you can do it with a convolutional layer, but that just it's fully convolutional and adapts.
I understand the question, but it's very difficult for me to give you an answer because the problem is I'm really not that knowledgeable in audio at all. Like I've been working with.
I'm just asking for some inventive answer here. So if your activation is variable length, or if you are not, or let's say you want to reuse the network for instead of 32 by 32, 36 by 36 image.
I don't know. Intuitively, I would think like maybe studying a bit what happens if you're trying to go for compression, I guess, also, or in general for or continual learning. Oh, okay. Yeah, I was thinking, okay, if you're working in the other direction, maybe studying first a network that has larger intermediate embeddings so that you could notice like that. But I was thinking on compression, but on continual learning.
That's the problem. I think that our approaches are a bit constrained in that regard. Well, but this is also a problem of the course.
So is any of these, so some approaches look at the full signal, right? And some of them are using something similar to LSTMs or recurrent networks, I guess. It's, yeah, but then it's very tricky because I remember I reviewed that paper with continual learning for recurrent networks. The results looked promising, but everything was on tiny data sets, right? Like compared to MNIST permutations and stuff like that. And the problem is everything I was looking, it's like it looks promising, but it's this tiny box where I really don't know how you do that on moving. I would say, I mean, I don't know. I also have the feeling it's good to know that if I had the answer, then I can call you for having. It seems like it's interesting on your field, right?
No,
like
it makes me think that maybe we have to leave these activation-based masks behind if we want to deal with these other problems.
But I guess you've been trying, but working on activation masks instead of weights for LST or recurrent networks, the little experience that I have, it's a nightmare. So that's why I'm not sure. I have the feeling that maybe you could, if you have a problem where you could compromise and maybe think of something more like like task incremental learning, then I don't know if something like is proposing, you were proposing or the, so that you allow less, but you're only learning like the shift and like the bias and the normalization, right? Like the shift and the, this is better than such a small, and that it's better restricted instead of giving it the freedom. Notice also when training had that sometimes at the beginning, well, you have it in the study, I think in the supplementary material, right? Like how it hoards the activations and then it starts, the compressing starts happening later. I don't know now with these systems, this is doable without restricting one.
Let's move on.
Yeah. Yes.
In your approach, you divide the network capacity per task, let's say, no? So
Yeah.
you know that you're going to perform like 10 tasks.
Yeah.
And then you divide evenly, I understood.
Yeah.
And then from this division, you further use these growth percentages.
No. The growth percentages are these divisions.
Okay. And then how do you do it? You train n times to decide which growth percentage is more appropriate at the first task?
Yes. So the thing is, I could choose it, and I could choose the best partition, but that seemed unfair. So what we did is we came up with a framework. It's similar, like the idea is a bit similar to what we propose in the continual learning one. What you do is when you want to, on a validation separate test where you would learn with the network being added 5%, 10%, 15%, let's say, increments of 5, I think was the most common one. And then you allow a maximum, because if not at the beginning, like I would say, okay, up to 20, that's the maximum. And then you will look at the probabilities and you will choose the best probability. But if you are in the range of 1% of the best probability and you're lower, then you will pick that one, because the 1% on the validation set is good enough. And this way, for example, the results in flowers, I didn't put it in the paper because I thought I would get questions about it. But our results on flowers are with the network being 70 or 80% of the network. It didn't even 100. Like it got enough with that. The data set is more simpler. I mean, we look at the compression. We also saw that it did, like activations were compared to ImageNet, it seems simpler. So I think that's the thing. And this is what we were doing, like for making it comparable. And then we had the separate.
But then I was wondering if it's comparable to other approaches that just train once
Yeah, but I think I consider it fair because it's the same validation set I was using for the hyperparameters of the others. The others I was also training several times because I was changing the lambdas, or like in the case of, for example, PACnet is the easier example. I was doing exactly the same with PACnet, where the compression was set to 90%, but I also did some experiments where I was allowing to train 3 times. I didn't try more because PACnet was very clear that it has to be these numbers, or else if you have more than 4 tasks, you run out of network. So that's what I did with PACnet. The thing with PACnet is that it seemed extremely consistent with the 90%. It didn't choose 95 or 85 almost ever. It was like, I don't know, the constant. Yeah. And we don't need any hyperparameter for our method except for the, because we don't have the loss, right, or you have the L1 norm or something, we don't need that here. So it seems fair to me that we would have the same treatment, just like the hyperparameter.
Yeah, you're right. 2 more on catastrophic forgetting.
Oh.
Evaluation, you consider this data, this semantic task grouping, let's say, but I would say, why didn't you go to totally different tasks? I mean, to me, that's the more challenging scenarios. So you train on CFAR, then your next task is SVH.
Oh, yeah.
Next task is
multiple data sets.
Yeah.
Okay. Yeah, multiple data sets is something that we tried. We got some results, but we got them when we had already finished our work. We were trying with basically birds, flowers, and this data set, and then we were working with these semantics on Tiny ImageNet. And that's what we had. We forced, let's say, before publication, we were saying, oh, let's add ImageNet, because this will be a big thing. And it was not until we got the reviews later on that one of the reviewers was asking the same question. And I think it was when we were doing this, some of the other papers were not necessarily the ones we're comparing, like mass and so on were doing it, but it seemed like the scenario was different from what we wanted to do. And the intuition was that maybe it will be more difficult that our method will do well with the restriction that we don't, if we wanted to do the multi-data set, we were thinking we will do the AlexNet with 8 fine-grained data sets. But the problem is that a scenario in particular, it's very tricky to learn the first tasks on a constrained, if we were able to use our method normally and then we give it 50%, and then it will grow, maybe smaller, maybe not later, but it seems to be. Yes. So I had some initial experiments because we predict that the new batch of reviews maybe will mention the same. And our results were pretty good. We were doing comparable to PACnet and HAT. PACnet was doing especially well under that setting, which is always a bit confusing because I would think that something more like Piggyback that has a bar bone would do better when you shift. But PACnet from scratch was still doing very well. And HAT was also a good, something that was doing well enough because, the main problem we were seeing with HAT is that it took me a while to be able to use it on the larger input size data sets. When you were proposing the article, mostly was the smaller input. And the bigger one, it was not so easy. It was becoming a bit more susceptible to these sigmoids and how much it can compress on it. So in HAT, I saw that the same problems that HAT was having probably will come for us, right? Because it's also activation in the end. So, and we are more.
The advantage that you don't learn the compression at the learning stage.
Yes, and this is the advantage that for me was why I was excited about our method and I like it. But over the time I presented, I realized that there's a lot of people that don't value that because they don't realize that you can expand, we didn't, but you can expand it as much as you want. We limited our own method in order to make it comparable. people sometimes look at the numbers and it's like, oh, it's not so much, and don't realize that we can really get very good results in if we are able to grow. But so potentially can other methods which I've tested mine, but I've not been testing the others and so on. So this is a bit the point of it. Yeah.
Next question on positive transfer. So you know that when you do this multiple task setting, especially if you consider different data sets, a sequence of data sets,
yeah,
you would expect performance on, let's say, the second data set to be larger just because you have trained on the first data set than if you just trained from the second data set alone.
Yep.
I don't think you quantified that in the thesis or in the paper. Can you say something about it?
Yes. So I think it was a bit tricky because in order to evaluate that, sometimes you have to do several, like compare several baselines, let's say, that you have to do. And the limitation that we were putting on the method with the growing thing made so that I was not very encouraged to have to run several runs of the growing. Like the final versions of it were extremely long because I was running hat, PACnet, and hours with all of these hyperparameter ranges to pick the best one before moving into the next task. So that's why we were not. And also because I thought, I don't know if I want to give the forward transfer, which sometimes is difficult to quantify in some way. And when our method has the difference with hat, for example, that it doesn't have backward transfer. Like this is something that we would consider the drawback in some scenarios. I think that if you've learned enough, that's good, but it's also like the continual learning, I consider that this is something that zero forgetting cannot give, which is backward transfer. And yeah, in this sense, that's why the decision was that it was expensive, and we thought that putting I don't remember which figure was it. There's this figure that was putting the curves at each task, and indirectly you can see how the performance changes of each task at each time point. So even if the numbers are not there, you at least can see if the curve is going up or down. So this will be the forward transfer that we observe at some point. Yeah.
Then for cross-incremental learning, I have two questions, but a bit many. For auto-distribution,
yep.
And with that, a couple of questions and I'm finishing. You consider the case of classification-based neural networks for these, but there are a lot of tasks which are not based on classification. I don't know, I mean, in computer vision you have many of them too, so like producing object bounding boxes or in painting or any generative task, and these may benefit as much as the classification tasks from an auto-distribution detector or from an anomaly detector. But then your approach is cool because you depart from cross entropy and the softmax trap and all these things and go to metric learning. But I would tease you a bit and say you don't depart enough, because then you have all these bunch of tasks which don't really have classes, and therefore you don't have a loss if you don't have classes, right, with your method, and it doesn't generalize to this more broad category of auto-distribution detectors. So what would you say?
Yeah, I mean, yeah, I will admit it. I'm a classification, image classification guy. Okay, I mean, there's two broad, let's say, personal reasons. One of them being that we were working on those projects, but at the same time, we were having these connections between continual learning, out of distribution. So at a personal level, it was like the projects we were doing were focused on image classification. You see in the compression one that we did show that it worked on object detection because faster CNN was like the boom at that moment. It needed to be done. In the case of the out-of-distribution, we were also working on other projects that are not disclosed, and I don't know how much I can say. Yeah? Okay. So we were working with something that will use object detection. So the idea will be that we actually apply that, like the method that we're proposing, since it's on embeddings, if you want to play to bounding boxes, then instead of tackling the bounding boxes, you can still get the bounding box and apply the out of distribution at that point. So it can be a step after. And since that was possible, then I personally didn't explore directly, as it can be an extra step that you can put afterwards, because you'd only need the outputs of the system, and in this case it was an embedding for each bounding box. It was not like the bounding box generation was not included in this, and then we will apply it per bounding box. But I agree that I don't know how easy it is. I think it will be fun though to just try it, because in the end, one of the things I like the most is that I think it's quite simple strategy, and it's just pointing out, hey, we have this tool since 2006 laying around, and look how powerful it is. So yeah, but I would say the personal reasons of focusing on other topics is why I didn't explore more this idea. I don't know if that answers.
Final question.
Yeah.
In your approach, you define auto-distribution data somehow. You say we use the background, or we use Gaussian noise, or
Yep.
etc. And this is used during training, also this data and this criterion. To me, it seems an important decision that is worth studying. So if you do something else, or you know something else, or how these impacts, how different choices have an impact on...
Yeah, we were also, I agree. Yeah, if you're going to use unlabeled data, the distribution that you're trying to push away is important, I would say. And here is what we were saying, right? Like when we were trying these on the traffic signs, and then instead of traffic signs, we were using background patches or noise, I intuitively thought background will do much better than Gaussian noise, right? Like,
okay, because this false positive rate is of the noise itself, or
of this distribution.
this column is what you use as auto-distribution data for training?
No, the one that is used during training is the one that is in bold and says seen.
Okay, now I know.
And then we evaluate on the three of them, the one that you see and the other ones.
Okay. Then I didn't have a proper look at this table.
Okay. And then I would say ignore background and noise, because these are just pointing which distribution we are checking. But if you look at the Tsinghua, which is never seen in both in these two rows, Tsinghua images are not shown. So if you have seen background, you do worse in Tsinghua, like even comparable to when you were having cross entropy, while if you use Gaussian noise, which is the cheapest distribution that you could get, it does comparably well. I mean, it's comparable to even not using out of distribution. So I think it's interesting. But both of them seem to not help that much in this case. So if I would choose, if I don't have something that is related, I would rather just use like the contrastive loss without having to add an external data for out of distribution.
Because then with this contrastive loss, at least with triplet loss, we have this, we know there are these strategies of hard triplet mining, semi-hard triplet mining, etc. Could something here be...
For sure. It just, we decided on using the contrastive because the results were so clear that we wanted to, and contrastive is a staple, right? Like a lot of people know what it is. So we thought if the results are like this with contrastive, imagine, like it was, for me, or I saw it a bit as an encouragement. We also tried a few things. But yeah, it sometimes depends. Like hard mining, it's good for some, also for some problems, and some other not. So I would say you probably can get much better results than we get by just choosing the specific metric learning, mining, and loss being tripled or whatever for the specific problem that you're doing. But our point was more general, saying metric learning is, look at it in broad terms. Yeah.
Okay, then that I finished my questions. I would just like to end by congratulating you for your hard work and your good work during these years, and congratulating the supervisors for also their hard and great And let me just finish with a thing that I like from the thesis and from your work, and it's that your approaches are simple, very simple. And I say it as a praise. I say it as a
I take it as a praise.
positive way. So if you need to complicate things a lot, the result might be great, because otherwise I don't like dealing with all that complication.
Yeah.
But in your case, it's the opposite. So you propose super simple things that work, and that work very well. So, and that's a feature I always praise in people. So thank you.
Thanks a lot.
Okay, now the committee stays.
Yeah, so now the committee stays in the chat. Well, no, first of all, we need to ask, I think, if there is some doctor in the room who wants to ask some questions.
No doctors here, so.
Then let's go to the next step. So the committee will deliberate here. So we ask you to leave the room and leave the Teams channel.
Yeah.
Okay, I will mute my Teams channel so that it's available when I come back directly, if it's okay. Or, well, I can leave also.
Ah, yes.
I leave it?
Yeah.